We're going to now graph each absolute value equation and state the given characteristics. For number 8 in our test study guide, we have y equals the absolute value of x minus 4, then subtracted by 1. Remember, when we're graphing, we want to pull the opposite number of the inside for the first part of our vertex, and then we'll take the actual number for the second part of our vertex. The vertex point is at 4, -1, so I plot that point accordingly. From here, I have to always do the slope on the right side that matches the front of my absolute value. I like to use these quotations for slope because remember, I'll be doing that slope of 1, up 1 to the right 1, on the right side of my absolute value. But what's going to happen now is I'm going to have the opposite slope on the left side. I must mirror that graph here to make it a V shape. We connect all the points with a nice straight line, one side to the other, and you see that V-shaped absolute value forming. The domain is going to be all real numbers here because we have an arrow on the left and an arrow on the right side, and you can write it in either interval or set builder notation. Range is going to be talking about the lowest y value, which is going to be -1 here. Square bracket because it is included, it's a fill point, going all the way to infinity because we have arrows at the top of our graph. And again, you can do interval or set builder notation. The range in set builder notation is read as the set of all y such that y is less than or equal to -1. For my increasing interval, I'm going to look at the part of my graph where I have a positive slope, so that would be this right side. When I write intervals, I always have to use the x value, so sometimes I like to make a reminder for myself that I will use the x values when I'm writing the increasing and decreasing interval. So that's going to be where I highlighted starting at the x value of 4, going to infinity. No brackets for an interval because you can't increase at a single point. We go ahead and have decreasing be where we are having a negative slope, which is going to be the left side of my graph here. That's going to happen from negative infinity to, again, that x value of 4. Again, no square brackets because you can't be increasing at a point. We go ahead and see that we have our x and y intercepts on our graph. We're going to name them as points. The x-intercepts are 3, 0, and then 5, 0. Where's the y-intercept? Way up here at 0, 3. Let's go ahead and graph number 9. We again go ahead and pull our vertex point. That's going to be the opposite of the inside, so a -1. Then the actual value of the outside, -3. The vertex point is -1, -3. From that vertex point, we do a slope here. Remember, that's going to be the slope on the right, a -2. How we do that is go down 2 and to the right 1. I would keep going. Obviously, my graph kind of stops there. But then don't forget to mirror it on the left so that way you get the actual absolute value V shape here. Domain again is going to be all real numbers because we have an arrow on the left and an arrow on the right, or an interval notation that was -infinity to +infinity. Again, you can use interval or set builder. Range is going to be talking about the arrows going down, -infinity, stopping at the highest y value of -3, square bracket. Set builder notation, that inequality in that set builder notation is going to be less than or equal to -3. Increase and decrease here. Again, we're going to go ahead and highlight where we have a positive slope for increasing. That is the left side. X values again, because it's interval, -infinity to the x value of -1. Then we're decreasing on the right side of my graph here from the x value of -1 to infinity. Again, decreasing interval, look at that negative slope. There's at no point where it crosses the x-axis, so there's going to be no x-intercepts. But we do have a y-intercept here. Count it down, you were at 0, -5. Two more graphing examples here. We have number 10 being y equals 3/4 absolute value of x plus 2. Remember, first step is to pull the vertex from the inside. If there's no number, it's a 0. And then we're going to go ahead and pull the actual value outside, which is 2. 0, 2 is our vertex point. Slope, again, is going to be what happens on the right side here. So that is 3/4. So that means I go up 3 to the right 4. I then want to mirror that on my left side and graph an absolute value graph, making sure it has that V shape, a true characteristic of an absolute value graph. Domain, again, is going to be all real numbers. You can write it as -infinity to +infinity, or in your set builder notation. Range is going to be talking about the lowest y value, which is this point here at y being 2. And then the highest thing on my graph is arrows that are going to keep going to infinity. In set builder notation, our inequality is going to be greater than or equal to 2. Make sure you have those equal signs and square brackets since that point is included. We go ahead and graph our increasing interval by highlighting that positive slope here on the right side. Again, we're using the x value, so I'm going to say it's increasing from that point where the x value is 0 to infinity on the right. Decreasing is going to be that negative slope, happens on the left side over the x values of -infinity until 0. X-intercept is going to be none again. It doesn't pass the x-axis. But the y-intercept is going to be that point we have here at 0. Let me make that more bracket-like, 2. The next example is graphing y equals -3/2 absolute value of x minus 3, where again we pull the vertex first. So I do the opposite of the inside, which is going to be 3. And then I pull exactly the number from the outside, but when there's no number, it's 0. So we plot that first vertex point at 3, 0. The slope is going to be -3/2. Remember, I put that in quotations because that's what I'm going to do on the right side of my graph. So on the right side from the vertex, I'm going to go down 3, right 2. But on the left side, I'm going to go down 3 and left 2 to mirror that slope and make it an absolute value V shape. The domain is going to be -infinity to infinity, an interval notation. In set builder notation is the set of all x such that x is an element of all real numbers. And the range in set builder notation is the set of all y such that y is less than or equal to 0. -infinity to 0, remember range is the y values from bottom to top, square bracket on 0. Interval notation here now. We're going to have increasing interval be where we have a positive slope, and that's going to be happening on the left side of our graph. X values it's happening over is going to be the arrow from -infinity on that left to the x value of 3. Then I have my decreasing interval happening on the right side of my graph after that vertex of 3 till that arrow all the way on the right side, which means infinity. We go ahead and talk about the x-intercept being 3, 0, and then the y-intercept here, it is going to be a decimal. So we're going to say it's at 0, -4.5. Next in our test study guide is piecewise functions, where we'll evaluate the piecewise function below for the given value of x. This is where I'm going to color code here, because any x value that is less than -2, I will plug into the first part of my piecewise function. If I have -2 being less than or equal to x being less than 6, I will go ahead and plug it to the middle part of my function. And then if my x value is greater than or equal to 6, I will plug it into the last part of my piecewise function. So let's look at the first value of x given. 13 wants us to find f of negative 4. Well, negative 4 is going to be less than negative 2, so I'm highlighting it in red. Plug that negative 4 into my first line, but that first line, always and forever, no matter what x value I'll input, will give me an output of 5. So 5 is my answer. Number 14 is f of 6. Be careful with this one because it has to be where the x value can be equal to 6, and that is in purple only. That's in the function of negative 2, x plus 10. But remember, I know my x value now to be 6, so I erase and replace that x value with a parentheses of 6. Solve with your PEMDAS or GEMDAS order of operations, which means I multiply first to get negative 2 times 6 to be negative 12, and then I add negative 2 plus 10 to get, negative 12 plus 10 to get negative 2. I was getting ahead of myself with the answer. Negative 2 is going to be the x value for 15 because it's f of negative 2. Only place where negative 2 is equal to an x value here is in my second line, so I'm highlighting this a green. I'm going to plug this into my second line part of my function. That part of my function is 1/2 x minus 6. Remember, I place the x with a negative 2 and keep everything else. I like to multiply a fraction across a fraction, so I'm going to put that negative 2 over 1 so I can multiply straight across the top. 1 times negative 2 is negative 2. And straight across the bottom of my fraction, 2 times 1 here, 2. And then I subtract 6. From here, I divide negative 2 by 2, which is going to be negative 1, subtracted by 6, which is going to be negative 7. Last one, number 16, is going to be f of 0. 0 is going to be satisfying that middle row that's green. So I'll input 0 into the 1/2 x minus 6. So it now reads 1/2 times 0 minus 6. The multiplication comes first. Remember PEMDAS or GEMDAS. 1/2 times 0 is 0. 0 minus 6 is negative 6. So again, I'm going to evaluate this piecewise function. Whenever x is less than or equal to negative 7, I will input it into the first part of my piecewise function. Whenever x is between negative 7 and 4, I will plug it into the second part of my piecewise function. And then whenever x is greater than or equal to 4, I will plug it into the last part of my piecewise function. For 17, g of 9 is what is given. The x value is 9, so that's definitely greater than or equal to 4, which is going to be my purple. Negative 4/3, I replace the x with a 9 plus 1. I now am going to help myself by putting 9 over 1. I cancel out my 3 because when I divide 3 by 3, I get 1. And I cancel out by 9 because when I divide that 9 by the same 3 value, when I'm crossing here to simplify, I get 3. And then I can multiply straight across the top. Negative 4 times 3 is a negative 12. And notice in the denominator it's just 1 times 1. We know 1 times 1 is 1. Negative 12 divided by 1 is really negative 12. So I'm going to skip that step and just have a plus 1. Negative 12 plus 1 is negative 11. G of negative 10, that x value is less than or equal to negative 7, so it gets input into the first part of my piecewise function. 2 is the absolute value. Instead of x, I have a negative 10 minus 5 plus 3. Order of operations tells me to do what's inside the absolute value first, which is negative 10 minus 5 to make a negative 15. When I take the absolute value of negative 15, that's actually going to be a positive 15 since the absolute value is the distance from 0 on a number line. And then I multiply, then add 3 to get my final answer to be 33. For number 19, again, that x value is -7, so that will be indeed less than or equal to -7, meaning it's getting input into the beginning part of my piecewise function. 2 times that absolute value. Instead of x, I have -7, subtracted by 5. Close that absolute value up before I add 3. So again, order of operations tells me to get the inside of my absolute value down to one number. -7 minus 5 is -12. When I actually take the absolute value of -12, remember again, that's the distance -12 would be from 0, which is 12 spaces away. Order of operations tells me to do the multiplication of 2 times 12 to get 24 first before I add 3 to get 27. Last 20 here for this piecewise function tells me g of 1. That is going to satisfy my green criteria, my green restricted domain of x being between -7 and 4. So instead of x plus 8, I have 1 plus 8, which is going to be 9. I'm going to graph the following piecewise functions. I always start by drawing a dotted vertical asymptote at my restricted domains. So x is less than 3 and x is greater than or equal to 3, which is why I draw a dotted line where x is 3. From here, I'm going to graph each one separately. So I'll again color code here. I'll do pink for the first one, telling me it is f of x equaling -1/2 x minus 1. So that is y equals mx plus b, so I have to start at the -1 here. Then I do a slope of -1/2, and I graph a few points. Remember, I like to make the inequality into an arrow. Since its x is less than 3, if I make that into an arrow, it's pointing to the left. So that means I have to erase and replace everything that's not on the left side of my equation. And since it's just less than, I will cut this off at an open circle on my vertical asymptote here. And again, erase the right side. What I'm going to replace on the right side with is going to be this other function, because the other function happens when x is greater than or equal to 3. So that will be on the right side again to make it into an arrow. We start that at -7 as the y-intercept, and then I have to do a slope of 3. Again, I just talked about how this is only going to be appearing when x is greater than or equal to 3. So I erase everything on the left, keep the filled point on the x value of 3. That dotted line there represents that x value of 3. And I keep everything on the right. Next one, number 22, is going to be g of x equaling the piecewise function of 2x plus 1 if x is less than -2. As well as g of x equaling the absolute value of x subtracted by 3 if x is greater than or equal to -2. So both have the -2 stated in that inequality restricted domain statement. So that's going to be where my vertical asymptote places. We're going to go ahead and have x being less than -2, which is going to go ahead and be to the left, because when I have a less than, I can make it into a left arrow. From here, I need to graph 2x plus 1 that starts at the y-intercept of 1 and continues to happen with a slope of 2, which means I go up 2, right 1, or I can do the exact opposite, which is down 2, left 1. Because it's only happening when x is less than -2, I have to erase everything on the right, and I also have to erase and replace that filled point on my x value of -2 with an open circle. Can't be equal to, just less than that -2. On the right side of my graph here, I'm going to go ahead and have my absolute value graph of x in that absolute value subtracted by 3. Remember, for an absolute value, pull the inside number to be the x value of your vertex, and then the outside number after your absolute value is the true number for the second value in your vertex. We're going to go ahead and do the slope. There's no number in front of x, so it's just 1. And I mirror it on the left side. It does have an equal to, so I'll go ahead and keep a filled point for this part of my graph here when my x value is -2. And since it's greater than, remember I can make it in an arrow showing it's going to be happening on the right side here. 23, I'm going to go ahead and have vertical dotted asymptotes here at 0, 2, 4, and 6. So again, let's graph them in at 0, 2, 4, and 6. Why I need to graph them there is because that was all the numbers in my restricted domain inequality statements here. Let's read these piecewise functions here. We have h of x equaling 3 if 0 is less than x, less than or equal to 2. H of x equals 1 if 2 is less than x, less than or equal to 4. H of x is -1 if 4 is less than x is less than or equal to 6. Okay, so each one of these are going to go ahead and be a horizontal line. So the first one here, I'll highlight in pink and graph in pink. I'm going to have a horizontal line at 3. Specifically, that horizontal line is going to happen between 0 and 2. Since there's no line with 0, I'm going to have an open circle, but then a filled circle on the right side since I do have a line with 2. Next part of my piecewise function, I'll go ahead and graph here, is going to be 1. And that's going to be a horizontal line at 1 when x is between 2 and 4. Open circle on the left side since it is just a less than by that 2, but it's less than or equal to by the 4 part of my inequality statement, so I put a filled circle. And then last horizontal line is going to go ahead and be -1. That happens between 0 and 4. Open circle at 4, since it says 4 is less than x, but less than or equal to 6. So the equal to by 6 in our inequality statement, we put that filled circle. Last example, number 24, is f of x equaling the first part of my piecewise function happening when x is less than or equal to -3. What I have it in, or graph it in, is 2 with the absolute value of x plus 5. After that, I have an plus 3. Then, if I have -3 being less than x being less than or equal to 4, I'm going to go ahead and have my graph be just f of x equaling x here. And then again, last part of this is going to be when x is greater than 4. I'm going to have f of x equaling -3x plus 7. So, first part is to draw those vertical dotted asymptotes at -3 and 4. Those are the two numbers I just read in my inequality statements, so I put my vertical asymptotes on those x values accordingly. First part of my graph, again, is going to be grafted on the very left side of my -3 vertical asymptote there. But how I graph that is, again, an absolute value. Remember, for the absolute value, I have to pull the opposite of the inside first, and then I pull the actual number to get my full vertex of -5 up 3. -5, 3 is indeed my vertex point. My slope is going to be 2, so remember I go up to right 1 to mirror it on the right side of my graph. and I go up to left 1 again to mirror the right to the left. I have to stop this graph when x is equal to -3 because that's where my inequality is stopping, where my domain is restricted. And it is going to be a filled circle because I have x being less than or equal to -3. So filled circle, filled point there. Then I'm going to go ahead and graph f of x equaling x. Remember that means I start at the origin because it's still y equals mx plus b format. But I can't go anywhere. I have to start at 0. And I have to still do a slope of 1. Means I can go up 1 to the right 1 and down and to the left. Okay, it's only happening where I have -3 being less than x. So that's an open circle at -3. And it keeps going until I have x being less than or equal to 4. So I'm filling a circle on that x value of 4, on that vertical dotted asymptote there. Then I go ahead and graph my last function. It is x being greater than 4. So that's going to be to the right of 4. But specifically, I need to start always on the y-axis for slope-intercept form. So that is f of x equaling -3x plus 7. So the plus 7 is my y-intercept. I'm going to graph really tiny points because it's a -3 slope. I go down 3 to the right 1. And why I graph those tiny points is because I'm going to have to erase them. This graph is restricted to the main domain of x being greater than 4. So I have to erase any point on the left side. I keep the points on the right side, and because it says that it's just greater than, I have to do an open circle on my vertical asymptote, x value specifically of 4.